exam was a 92. So clearly it wasn't that bad. But yeah, so we're not gonna go over all the questions on the exam because one, I posted the answer key, which you guys can take a look at. And then if you really need more clarification, then just email me for office hours or something. But yeah, if no one has any other comments, then we'll just begin the next chapter.
Professor, when will we be receiving our grades back?
Tonight.
Okay.
I'll send it back through all of your emails.
Okay, thank you.
Okay, let's begin. So chapter 6.3. Chapter 6.3, the title is partial fractions. So this is going to be another method of integration that we will learn how to use. Okay, so again, like all lectures, we first need to motivate why we even need this method. So let's take a look at this integral right here. So hopefully everyone can see that. This is integral of 3x plus 11 over x squared minus x minus 6. And it appears that we don't know how to solve these type of integrals, okay? Well, not without, or we don't know how to solve it using any techniques that we know so far. Give me 1 second, someone asked for permission. Okay, so we don't know how to integrate these type of integrals. So what we've learned so far are U substitution. What else did we learn? Manipulating trig functions and integration by parts, right? So yeah, just take like maybe 10 seconds just to convince yourself that you don't know how to do this question right here. All right, everyone should have permission to record now. Just a note, if you're try to be on time if you're going to request for permission to record, because then I have to keep stopping myself to give you permission, okay? So just be mindful of that. Yes, this is chapter 6.3. All right, so once you've convinced yourself that you do not know how to do this question, let's move on. All right, you guys should be convinced. So now let's consider this integral right here. This should be something that we do know how to solve. So take a look at this one. Does anyone know how to solve this integral, by the way?
Do we separate it into two different integrals and then solve it?
Yeah, you could just do each one separately. So the first one, 4 over x minus 3, what's the integral of that? Anyone know? Yeah, so it's just the ln integral, right? If you take the 4 out, then you have 1 over x minus 3, and that's just ln of x minus 3. Okay, so these we know how to solve. Let me just make sure that, yeah, so I have the solution on this slide right here. It's 4 ln of x minus 3 minus ln of x plus 2 plus c. Okay? So we know how to do these. All right, and now here's the cool part. It appears that the integral we just solved right here is actually the same thing as the first one I showed you, okay? So the integral of 3x plus 11 over x squared minus x minus 6, as well as the one we just did, those are actually the same thing. So you guys might be wondering, well, how is that even possible? And well, I'm glad you guys asked. So what we're going to do now is just convince ourselves that these two are the same integral. All right, so let me open something to write with. Did any of you guys knew that they were the same integral or no? Yes, no? I mean, it's not obvious for sure. By the way, Alice, how did you know?
I studied BC last year on my own.
Oh, okay, so you cheated. All right, fair enough.
Well, last year.
All right, so right now we're just going to convince ourselves that they're the same. So in order to simplify the right-hand side, we need to subtract the two fractions. We're going to need common denominators. So let's get common denominators. X minus 3, x plus 2. Okay, so simplifying the numerator, we should have 4x plus 8 minus, this right here is x minus 3, right? So if I distribute the negative sign, this will be minus x plus 3. Okay, and then denominator, and then we have 3x plus 11 over our denominator. And you guys can verify that the denominator is x squared minus x minus 6.
Wait,
Okay?
James, what did you just do over there? Like, I literally lost you. Like the one with the x minus 3, x plus 2. Like, what did you do?
Oh, so this denominator, sorry, this numerator here is x minus 3, right?
Right.
So this should be in parentheses, technically. And then I distributed this negative sign.
Oh, got you.
So then it becomes minus x plus 3.
Got you.
All right, so this is to show that these two expressions on both sides of the equal sign are the same. So this is very useful because if we learn how to split apart fractions like this, we can integrate things. So this brings us to the question of, well, how do we actually do that? Okay, so right now what we're going to do is we're going to just go through the process of doing this question from scratch, and then once we finish the question, then we'll generalize the process. So let's do that. So here's our question. All right, so this is how it goes. First, we're going to just factor the denominator and see what we have there. So this becomes 3x plus 11 over, let's see, how do I factor this? So the only way to get x squared is x times x. And then minus 6. How do I do this again?
X minus 3, x plus 2.
X minus 3x plus 2. Is that right? I'm going to take your word for it. Okay, so you factor the denominator. And then what you guys want to do is you want to basically make a separate fraction for each factor in the denominator. So this is going to be some side work. We want to rewrite our original integrand, x minus 3, x plus 2. We want to rewrite it as one fraction with this denominator plus another fraction with the other denominator. And the reason why we're doing this is because if we can figure out what these two fractions are, we can integrate. So right now we don't know what the numerators are. So what we do is we just give them constants. So I'll call this, I don't know, A, we'll call this B. So our goal is to find what A and B are, okay? Now, how do we do that? Well, we said that these two things are equal. So if they're equal, then let's try to simplify the right-hand side. So the right-hand side will be A times x plus 2 plus B times x minus 3 over our common denominator. So this is what we have so far. So feel free to stop me if you need any more clarification on any previous steps. But here we have two fractions and they're both equal to each other. Their numerators, well, their denominators are the same, right? So if their denominators are the same, then their numerators also have to be the same. So we can conclude that 3x plus 11 is equal to the other numerator. All right. So remember, our goal is to find what A and B are. So let's continue this. So I'll distribute, I'll get AX plus 2A plus BX minus 3B. Okay. Now, does anyone see a way for us to solve for A and B?
Use the roots. So plug in each root individually.
What are the roots?
X equals 3 and x equals -2.
Yes, that works. So one way to solve for A and B is to just take a look at these factors here, this x plus 2 and x minus 3, and just choose very specific values of x that would make it easy to solve for. So because our equation holds for any value of x, right? So if we just choose x equals -2, then what happens? Then we will have 3 times -2 plus 11 is equal to a times 0 plus b times -5, right? So all we did was we substituted x into this first equation here. Substituted -2 for x. So if we simplify this, we will have -6 plus 11, that's 5, is equal to -5b, right? So b is -1. Okay, great. So we found one of the variables, b. Now we just have to find the other variable. So let's just label this. That'll come in handy later. All right.
James, so you basically just kept like the second thing, like the ax plus 2a plus bx minus 3b, you're just not doing that one?
Yeah, I mean, we didn't really need to do that
Gotcha.
for this approach, so but
Gotcha.
it's fine. Okay, so to find a, we can just choose another convenient value for x to get another equation, okay? So to find a, we want to basically get rid of this part of the equation right here. And to get rid of that part, we can just let x equals 3. So if x equals 3, then we have 3 times 3 plus 11 is equal to a 3 plus 2 is 5 plus b times 0. So we have 17 equals 5a.
Wouldn't it be 20? Since it's 3 times 3 plus 11.
Yeah, sorry. For some reason, I thought 3 times 3 was 6. This is 20. So a is 4. We just find the numbers cancel out one of the variables. Yeah, I mean, it's not the only way you can do this, because what we're essentially doing right now is we're trying to solve for 2 variables. So we need 2 equations. So this is sort of like solving a system of equations, which, you know, there's multiple ways of doing that. But this is one way. One note is that for some questions, this method might not be the most convenient. So I'm just gonna show you guys an alternate way to solve for a and b. So again, we already found a and b, but let's see how we can do it another method, which might come in handy. Going back to our second equation here. So this one. So I'm going to group the terms a little differently. So I'm going to write 3x plus 11 is equal to ax plus bx plus 2a minus 3b. Yeah, and I think someone in the chat was referring to this. But what we can do is we can sort of group the coefficients by their degree. So it's a linear function, right? This is 3x plus 11. On the right-hand side of the equation, there's two terms with an x. I can factor out the x. So I have a plus b times x, and then I have plus 2a minus 3b. Okay. Now, when I read it like this, can you guys see what two equations you can make out of it?
I guess you can make a plus b equal to 3x, and then 2a minus 3b equal to 11.
A plus b will actually just be equal to 3.
Yeah.
So yeah, so basically a plus b, this is the coefficient in front of the x, right? So that has to be the 3, and then the rest has to be the 11. So from this we can write a plus b equal to 3, and then 2a minus 3b equal to 11. And then you can solve this system of equations, and you should get the same a and b as we did before, okay? So we're not going to go through with it, but that's an alternative method. All right, so we have a and b, so let's rewrite the integrand. Where was it? It was over here. All right. So a is 4 and b is -1. Okay. So a was 4 and b was -1. All right, so we're pretty much done now. We rewrote the integral as two different fractions, which we can integrate. So who wants to finish this? Well, we already did it, so we know the answer, so never mind. This was 4 ln of, by the way, when you have a ln integral, sometimes it's good practice to put absolute value symbols, because if you guys remember, the domain of ln was the input has to be positive. So we can write x minus 3 in absolute value. And then the other one's -1. Plus c. Okay, so that's how a typical partial fraction question looks like. Any questions? Okay, so now let's generalize the process. Partial fraction decomposition. So whenever you're given a function in this form inside the integral, so f of x equals p of x over q of x, when the numerator and denominator are polynomials, and the degree of the numerator is less than the degree of the denominator, then we can do this partial fraction decomposition, okay? There are some cases where the degree is not less than the denominator. In those cases, you'll need to do long division before you do partial fraction. Okay, so unfortunately, we have to recall how to do long division for some of these questions. When did you guys learn that, long division? Was it calculus?
Pre-calc.
Pre-calc? All right, so you guys probably all forgot then. So we'll probably have to do some examples as we go forward. Yeah, so I mean, this slide doesn't really give much information. So, okay, there's this table here, which is basically a reference for how to set up your different fractions when you break it apart. So the one we just did, right? That one was when the denominator was, what was it? X minus 3 and x plus 2. Those are linear functions. So that's basically like the first scenario in this table. So when your denominator is linear, then you just write a constant in the numerator, like we chose a and b. Those are just constants. The second row of this table says that if you have a linear function that has a power, you need a specific fraction for each power. Okay, and then if your denominator is a squared function, then your numerator has to be a linear function. So it's not just a, it's ax plus b. And you also need one for each power if you have multiple powers for. Don't worry, this doesn't make sense right now. We'll just do some examples later. All right, so this one, we will, should we do this together or should I let you guys do it? Let me see. Yeah, let's do it together. I don't think we're ready for this yet. Okay, so here it is. Same process as, or similar process compared to the other one. First thing we want to do is just factor the denominator. So let's do that. This will be I can factor out an x, right? So if I factor out an x, it's 3x squared plus 4x minus 4. And then we can probably go further. All right, what can this be?
X plus 2 times 3x minus 2.
Let me see. X plus 2, 3x minus 2. So x times 3x is 3x squared. That's negative 4. Yeah, this probably works. Yeah, okay, sure. So those are your factors. Now we split it into multiple fractions. So we're going to need 3 this time. We need 1 for the x, 1 for the x plus 2, and 1 for the 3x minus 2. For the numerators, because these are all linear functions as denominators, we can just put constants, right? A, B, and C. So if we were to set up an equation to combine all 3, to add all 3 fractions, this would be A times the other 2 factors. So x plus 2, 3x minus 2, plus B times the other factors, plus C times the other factors, x plus 2, right? And this would be all over our common denominator, but we can skip that step and just go straight to the part where we set it equal to our original numerator. So here's our equation, and our goal is to solve for A, B, and C. So how do you guys suggest we solve for A, B, and C here? What will be the best method? So remember that because we have 3 variables we want to solve for, A, B, and C, we're going to need 3 equations. So I think the best way to solve this would be just to use the roots again. So pick very strategic values of x to cancel out some of the factors. So what can we choose for x?
0.
Yeah, so if we choose 0, then this term and this term will go to 0, right? Which gives us a nice equation. So if x is 0, we have a times 0 plus 2 times 3 times 0 minus 2 plus 0 is equal to 0 squared plus 4. Okay, so that gives us one equation, which actually we can just solve for a right here. So here we have a is equal to -1. Okay. What's another good value of x we can pick?
-2.
-2. Yeah. So if we choose -2, that will cancel out this factor, which will make the first term go to 0, which means we'll have b times -2, and then this is -8. This term would also go to 0, is equal to 4 plus 4, 8. So that gives us b is 1/2, I think.
Professor, I have a question.
Mm-hmm.
How did you get -1 for A?
Second. So here we have a times 2 times -2 equals 4. So that means we have -4a equals 4.
B and C are 0, so it just kind of cancels out.
Yeah, we plugged in x into this equation right here. So when x is 0, then this is 0, and this is 0. So the only part that doesn't go to 0 is this part right here and this part right here. Okay, so b is 1/2 here. And then is there another value of x we can choose to solve for c?
2/3.
3.
Sorry, can you read that? I didn't hear that.
2/3.
Over 3. Yeah, because we want to cancel out this term right here. So if x is 2/3, the first term goes to 0, the second term goes to 0, and we get c times 2/3, 2/3 plus 2 equals 2/3 squared plus 4. Okay, so now we have to actually like use our brains and add fractions. So this is 2/3. Uh, 2 is 6/3, so that's 8/3. This is 4/9. 4 is 36/9. So 40/9.
Yep.
Okay, so this is 16/9 equals 40/9. The 9's go away. So c is equal to 40/16. Okay. So we found a, b, and c. So that means our original integrand reduces to the following 3 fractions. So a was -1, b was 1/2, and c was 40/16. Great. And then at this step, we should be able to solve this integral easier, more easily. So the first one is negative ln of x. Let me just use as a value. The next one is 1/2 ln of x plus 2. And then what will the third one be? Does anyone know? How do you do that one? Well, yeah, I mean, 40/16 simplified is 5/2, but with a coefficient of the, when you integrate it, what would be the coefficient? I don't think it's 5/2 anymore. So let's do that on the side, because this one actually has multiple steps. We're trying to do this, right? 40/16, 1/3x minus 2 dx. We don't have to factor out the 3, but we do have to do something with 3 because this isn't just a regular ln form. what we need to do is do a quick u substitution. So let u equals 3x minus 2. So du equals 3dx. So if we do that, then we have 40 over 16 integral 1 over u, and then this is du over 3, right? So du over 3. So then this becomes 40 over 30, 48. 1 over u. So this is 40 over 48 ln of 3x minus 2. Okay. So that's your last integral. 40 over 48 ln of 3x minus 2 plus c. So basically what happened was the first one is a regular ln. The second one is also regular ln, but the last one, you had to adjust the coefficient because there's basically like a 3 in front of the x. So that's sort of like, you have to undo the chain rule technically. So that's why the coefficient, instead of a 40 over 16, it's a 40 over 48. You only plug in roots for their respective fractions. Yeah, that's basically the one of the most useful ways to solve for a, b, and c. Okay, where was the answer? The answer was over here. All right, any questions so far? Okay, so let's continue. All right, so we just did example 1. Let's look at the next example. So this one, yeah, let's try this one. All right, why don't you guys try this? So instead of doing the whole problem, why don't you guys just do up to the step where you have the, you set up the partial fractions, but don't solve for the numerator. So just have your, like get your a, b, and c's and all that stuff, but don't solve for it yet. So why don't you guys try that for this question? So just set up your partial fraction decomposition. And let me just go back to the slide where we have the table for how to do that. And let me put it all into one page. Okay, so here it is. The question is on top, and then the table for how to split apart the fractions is on the bottom. See if you can apply this table to separate the integrand. Okay, so I'll just give you maybe 1 minute to set it up, and then we'll set it up together. You guys know the course linear algebra, right? Do you have to take, what are the prerequisites for that course? Calc 3? Okay, so that means none of you have taken it yet. All right, let's try to set up the partial fractions for this question. So it's already factored for us, which is good. We don't have to do that ourselves. So how many parts will we have? So let's deal with the x minus 4 squared first. Do you guys know how that one would, or what that term would give us? The x minus 4 squared.
Is it x minus 4 and x minus 4?
Not quite. Well, I guess here's a better question. Which row are we in this table? Is it row?
Second one?
Yeah, we're in the second row. So we're in this situation, and this is squared, right, for this particular question. So when you have a linear function squared, it says to do this. So you're going to need one term, which is the power of 1. So that means the first fraction is just x minus 4. The second fraction is going to be the same thing, but going up a power. So the second one is x minus 4 squared. Okay, so that's actually how you would have it. And then the numerators are just constants. Okay, so we can just use a and b. So that's how you would deal with the x minus 4 squared. The last factor is the x squared plus 3. So which situation is that on the table? Yeah, it's the third row. It's when you have a quadratic equation. So in that case, we can just write it into the denominator. But the only difference is that our numerator now needs to be a linear function. So instead of writing c, I have to write a linear function. So I'll write cx plus d. Okay. So that's how you would set up the partial fraction for this particular question. So basically, if you have, to generalize it, if you have a power for your factor, you need a fraction for every single power, okay? So if this was x minus 4 to the third, you would have 3 separate fractions. You would have one for x minus 4, one for x minus 4 squared, and one for x minus 4 to the third. All right, let's try to continue this question now. Our goal is to find a, b, c, and d such that the two integrals are equal. So why don't we combine the 3 fractions to get an equation. So this is a times x minus 4 squared, x squared plus 3, plus b times the other factors, x minus 4, x squared plus 3, plus cx plus d times x minus 4. Do we need, actually, you know what? Our common denominator only needs x minus 4 squared. So let's see, how can we do this? Well, this is our common denominator right here. Which means for the first fraction, we don't actually need a square here. And for the second fraction, we don't need this part. X minus 4 squared. Yeah, that looks good. So what I did was I basically multiplied all the numerators by whatever factor they're missing. And this is equal to the original numerator. So x squared minus 29 plus 5. So in here, we need to solve for 4 variables, right? A, B, C, and D.
You forgot
Alright.
the x, James, on 29.
Oh, thank you. So we have to solve for 4 variables. I guess I'll make a comment right now that might be helpful. So it can get quite ugly when you have to solve for many variables, especially 3 or more. So those system of equations tend to take forever. On exam situations, I'll probably never give you anything more than 2 variables to solve for. But like the max I'll go is 3. Like I'll never do this because this will probably take forever.
Positive 4?
Yeah, because we have A, B, C,
Yeah.
and D. We have 4 variables we need to solve for. So what we're going to do is actually we're going to skip the whole process of solving the system of equations. I actually have it done beforehand, so let me just give you guys the coefficients. So it turns out that A is 1, and B is equal to -5. C is -1, and D is 2. Okay. So we're not going to go into the details on how to do that. It's basically 4 equations, and you're trying to solve for 4 variables, which no one wants to do. All right, so now given these values of A, B, C, and D, let's rewrite our original integral. So this would be 1 over x minus 4 plus -5 over x minus 4 squared plus cx plus d. So that's -x plus 2 over x squared plus 3. dx. Okay, so these 3 integrals, we should be able to do at least the first 2. The third one might take a little work, but let's see if we can figure out what the integrals are. Okay, so what's the first integral?
ln of x minus 4, the absolute value.
Yep. So this is equal to ln of x minus 4. The second one, that one's not an ln, but I think that one should be doable as well. What would be the second one? I can factor the -5, right? And then take the integral. So -5, let's do it on the side. So we're trying to do 1 over x minus 4 squared. How do we do that one? Does anyone remember?
U substitution or no?
I mean, you could, but I think we can do without it.
Mhm.
But I mean, if you were to do U substitution, you would just make the denominator 1 variable, right? Yeah, you could just rewrite it as like a negative exponent. So x minus 4 to the -2. So then the integral is x minus 4. You add 1 to the exponent and then you divide by the exponent. So it's that. So it's -5 times -1. Well, it's just negative x minus 4 to -1 power. Okay, so that's the second integral. Let me just simplify this. This is +5 x minus 4 to the -1 power. All right, so the last one is actually going to take quite a bit of work. The first thing we can do is just this, we can split it into 2 different parts. So instead of writing -x plus 2, I can write plus the integral of -x over x squared plus 3 plus 2 over x squared plus 3. I can do that, right? Okay, so how do we do the first integral over here, this one? Does anyone see how that one works? I'll give you a hint. It's something to do with ln. All right, so let's do it on the side. We are trying to do integral of -x over x squared plus 3. If you were to do a u substitution where u was x squared plus 3, you can just make the denominator one letter, right, u. But would that work? Let's see. Then that means du would be 2x. Do we have a 2x? Well, we have an x. So that, yeah, it does work because as long as we have the x there, it's fine. We can put the 2 on the outside. So this would be integral of 1 over u. Let me put the dx here. So du is what would du be? We're trying to get a -x dx. So it's du over -2, right? That'll give you -x dx. So this would be 1 over -2. So this integral would essentially simplify to negative 1/2 ln of x squared plus 3. Okay. So this turned out to be an ln integral if you were to do this following u substitution. Okay, and then let's look at the last integral. So now we're looking at 2 over x squared plus 3. Does that look familiar to you guys? So I can pull out the 2 in the numerator, and then I can take the integral of 1 over x squared plus 3. What does this look like to you guys?
It reminds me of the derivative of tan.
Tan yeah,
Sure.
so it's almost arctan, right? The only thing it doesn't have is that it's a 3 instead of a 1. So there, we can fix that, but it will require a little bit of work. What I can do is I can factor out a 3 in the denominator, which will give you 1 over x squared over 3 plus 1. I think that's right. Yeah, that's right. All right, so we made it a 1, but now the issue is like this is not u squared. So we need to do a substitution. So if you were to let u equals I think x over square root of 3 would work. Yeah, so then du is 1 over square root of 3 dx. So if you were to do this substitution, then you would get 1 over u squared plus 1 du. But then I have to remove this constant to the other side. So that's square root of 3 over 3. All right, so now it's in the form of arctan. I think you guys might have like a formula for this type of situation that you can use. You can use that if you like, but this turns out to be square root of 3 over 3 arctan of u. Which is square root of 3 over 3 tan of x over square root of 3. Okay, so that's our last integral. I'll just put it here. And then this is plus C. All right, so this one was a pretty involved example. Yeah, this one was pretty tough. I wouldn't expect you guys to do this on exam or anything, but hopefully you're able to follow at least some of the steps.
So you're not going to give us like these kind of questions on the test, right?
Yeah, so right now we're doing partial fractions. I think a proper difficulty would be, do you guys remember the first one we did? The one with A and B? So it's a little bit harder than that, but nowhere as hard as this. That would be like an appropriate difficulty for an exam. Yeah, that was tough. Most of the times when you do partial fractions, the separate integrals end up to be like ln of something. But yeah, well, we didn't finish this topic yet. So on the slide, let me go back to the slide. We just did example. Yeah, we did example 2. So we still have 3, 4, 5. We still have 5 examples. We still have 3 examples to do after this one. We're not going to do any more examples today. I'm just going to stop it here. Because we didn't finish, I'm not going to expect you guys to do the homework yet, but I will say that you guys can start the homework. So the homework has, I think, 11 questions, and you can probably start doing the first half, which will, help you refresh what we learned today. But yeah, I mean, this topic, the questions do take forever. Yeah, like it requires a lot of work, a lot of paper, but I have faith in you guys that you guys can get it. So we'll stop here for today. Probably in about an hour, you guys will start getting emails about your grade for the first exam. And if you're not sure like why you got a certain grade, do take a look at the answer key first that I posted on Blackboard, and then if you take a look at that and you still think something is wrong, like I graded something wrong, then just email me, and then we can have a discussion, like maybe if I mark something wrong or whatnot. How did you all do? You guys did better than I expected. So the average was a 92, and the most common cause of point loss was you guys not showing enough work. But yeah, the average was really great, which obviously means one thing, and that's the test was too easy. But yeah, so that's all for today. If you guys don't have any questions, you guys are free to go.
No, don't say it's easy, bro. You're gonna give us hard questions. We don't need that. We don't need that.
No, it was good. Like I thought that the questions were going to be a little difficult, but you guys handled it well. When's the next test? No idea. Could you change the homework due dates like someone mentioned? They're supposed to be due on the day of the exam. If you really do need extension, just email me. I will extend it by a case-by-case basis. Wait, what's to October 12th?
So on Lumen, it says that chapters 6, 7, and 8 are some of the chapter or sections from the chapters are due on October 12th. So I was just wondering if you can change that. So it doesn't say past due.
I actually have no idea what you're talking about. Let me go on Lumen.
Okay.
I think it was November 12th.
November?
12th. Yeah.
Okay. Okay, then I'm probably wrong.
What chapter was it?
chapter 6 and 7, I believe.
6.
Okay, yeah, it's 11, 12. Okay, never mind.
Okay, all right, we're all good. Okay.
And also, there was a chapter 5 quiz copy.
Yeah.
You didn't have to do that, right?
Yeah, no, that one is for students who have like permission from the Office of Accessibility to like do another quiz. Yeah,
Oh.
you don't need to do that one.
Okay.
All right, you guys are free to go. I'll see you guys next Tuesday.